Hello, my name is Alexander James Rice, and I work for Professor Zhongqi's group at the University of Michigan. Today I'm going to be talking about super MeV gamma ray time-encoded imaging. This work demonstrates the capabilities of our current time-encoded imaging system, which is known as MIRA, using the current Orion CZT detectors. So previously, the highest energy that was imaged using this technology was cesium-137, which has a 662 keV energy peak. In this work, I will demonstrate the capability to image energies as high of 1274 keV, which was imaged from a sodium-22 source. Time encoding imaging, for anyone that doesn't know, uses a coded aperture mask to triangulate the position of a source by tracing back the photoelectric absorption through a hole in the mask and goes back to the source. Time encoding imaging just adds in the element of moving the mask, in the case of the MIRA system, in a snake-like pattern to add in extra effectively information to be decoded later. The mission relevance, this project aims to allow TEI to be used in a larger application of sources. Right now, time-encoded imaging is generally only used for low energy sources, generally around 200 to 300 keV. This is because the mask that's used in MIRA's case, in most typical cases, is tungsten, which is good for absorbing gamma rays, but a lot of higher energy gamma rays will be able to penetrate through the mask. So this shows the capability of TEI still being able to correctly image higher energy, despite penetration through a large percentage of penetration through the mask for higher energy gamma rays. So the MIRA system uses a rank 79 MIRA, which is 79 by 79 elements of open and closed. And it's controlled by two stepper motors that move it in the X direction and the Y direction in a snake-like pattern. For this experimental setup, sodium-22 was measured at several different depths away from the mask, 30 to 40 centimeters. In addition, there were two other sources present. I will not be discussing them here, but they were done to look at enrichment ratios to compare uranium, what you would expect to see for like a uranium enrichment. That's why you can see another source right here, but I'm going to be focusing on the sodium-22 for the high energy MeV. For the results, so here you can see the image of the 1274 keV energy from the sodium source. There's a clear hot spot that can be made out. In addition, the depth that the source is from the mask. So in this image down here, the depth between here and here is estimated by the detector or by the program afterwards, as if it's an unknown, and it's estimated. And it's very accurate for the estimation. It becomes less accurate the further away the source is from the mask. So in the case that it is 40 centimeters from the mask, it estimated it at about 39 centimeters. In the case it's 30 1/3 centimeters away, estimated at 29.5 centimeters. This is the furthest depth we've gone so far, and it was showing 4% resolution or better, or 4% estimation error or better in every situation, generally closer to 2 to 3%. This impact, this project was initially undergone due to a collaboration with Y12, in which they wanted to be able to quantify uranium holdup in a variety of different geometries and locations with very little information given. So I wanted to be able to estimate where a source would be, the size of the source, and the activity of the source. And as it's uranium, one of the key energies from uranium-238 is the 1001 keV gamma ray. So this can be compared to uranium-235 gamma rays to determine the enrichment. So this work clearly demonstrated the capability of the mirror system to detect and image super MeV gamma rays, and I want to, in the future, test the capabilities of the system at longer depths, up to a meter away, and see what the resolution is and the estimated depth that the source gives. Thank you.